I believe we've covered enough for you to do your homework, so I'm just going to get a head start on the next piece of the work. And so we're going to look at, let's get the heading, confidence intervals, right? Let's look at confidence intervals. For the difference between two proportions. This is in chapter 10. This is the second one in chapter 10. The first one is confidence intervals for a single proportion. And what I'm going to do is I'm going to do a question from start to finish, and I'm going to do it by hand with my calculator, of course. And then we'll show you how you do it with Solve. And we're doing it by hand for the same reason we would do the single proportion one, is that we want you to be able to understand what the calculations are like, so that when you use Solve, you could say, yeah, I could do it by hand, but this is just so much more efficient. So we're going to have a story that I'm making up, and it's going to be a clinical trial story. And in this clinical trial story, it's going to be a double blind. Just so we can introduce some other terms. And how's this going to work? Well, in this pretend story, there is a new cancer treatment. And the first lot, they're going to get the old treatment. And it's a pill. And the new group, so these are called the control, right? And the second group is called the experiment, right? Experimental group. And they get the new drug, the new treatment. And it's double blind because it's a pill and you get it for cancer. And they base success rate on the percentage of people who are alive, say 5 years later, right? They measure success in different ways in the medical field, right? So those who took the old treatment, call them P1, there was 400 volunteers, and in that group, 300 of them were a success, whatever way they measured the success. And in the ones that got the new group, and there were 600 of them, let me pick a number here. Take me just a few seconds more. I didn't like the answer I got. Okay, 468 of them were a success. And that ends up being 78%. And this one here ends up being 75%. So would you agree that superficially, at least, the new drug is more effective than the old drug? Now, that in itself is not considered evidence in the statistics world, right? We would say it's not significant. And the reason why it's not significant, from our experience, every time you take a sample of 600, isn't there going to be some variation in the answer? Maybe the next time you do it with a new group of 600, maybe there's only 74% success rate. And the next time it's 75, the next time it's 72, and the next time it's 80. Won't there be a lot of wiggle room? Don't you get different answers? And they can vary by quite a few percentage points, especially if the sample's not huge. 600 is pretty decent, but it's not huge. And would you agree that 400, if you did that lots of times, couldn't that get better sometimes, maybe 79%? And then maybe next time it's only 71%. Because each of these vary, this is one snapshot. And that's not really enough evidence to prove that the new drug, right, is better than the old. And the reason this story happens to be a double blind is, can you imagine they made the pills look exactly the same, right? The same color, the same look. You can do that with pills, right? They're just material. So the people who are getting the drug, right, who took part in this trial, right, this clinical trial of 1,000 volunteers with that cancer, right? Some of them are very ill, some have just got the cancer in both groups, right? But they don't know what pill they're getting. Nor does the doctor, probably your own doctor, know which one you're getting. So he doesn't know if you're in the group that's getting the new experimental treatment or you're still on the old treatment, right? And that's what makes it double blind. And we like that because remember, the placebo effect can have an effect on percentages. Now, for certain situations, probably like cancer, I don't think it's that strong. I wouldn't expect much difference. But in other situations, the placebo effect has been proven to be very strong. In other words, it can change things a lot. So how would we set this thing up? Well, we want to get a confidence interval, and let's decide that it's a 99% confidence interval that we want. And we want to find it for the difference between the two groups. So the calculation involves us finding the difference, which in this case, and it's okay to be negative, is negative 0.03. Would you agree that there's a 3% difference between the two? 78% success rate, 75, right? 3% difference. The reason it's negative is 75 take away 78, right? It's negative. And the formula that we're going to use to get a 99% confidence interval is P1 hat take away P2 hat plus or minus. Can anybody remember how many standard deviations, and this is a very rough number, generates a 90? Agree, it's about 3, right? Actually 99.7, but it's a 3, right? So it's 3 standard errors, 3 standard deviations. We call them standard errors. You could, however, do 2.875. And you could do 2.875. And you might say, where did these other numbers come from? This here is a very rule of thumb, isn't it? 1, 2, 3 standard deviations. We use it a lot because it's easy to work with. These two numbers are more accurate. In other words, they give you an answer that's much closer to 99%. Technically speaking, isn't that 99.7? It's a little bit different as well. Some textbooks use 2.87 when they want to be more accurate. Other textbooks use 2.875. So I'm just giving you those two guys to show you that there are other versions of this. Now, this to me is a good reason why we should have got together in some conference in Paris 50 years ago, and they all got together and they all said, everybody, let's use this one. Because then won't we all get the same answer, right? Or if you like, use this one. But whatever one you decide to use, let's all use it. Well, that's gone, right? That chance is blown, right? That ship has passed. And so now we're stuck with choices. I would agree 3 is easiest to do. Would you agree? But these two also work. When you use salt, I'm not sure which one of these two salt uses, but I do know for sure it uses one of them, right? So do you want me to pick 3? Do you want me to do the 287 or the 2875? Doesn't really matter because we're doing this by hand and then we'll do it with salt. But which one do you want us to use anyway? And I'll do it.
Three.
Brendan is lazy, thank you, because it makes my life easy as well, because times something by 3 is just less work, right? Now, there's one calculation I already know, right? We've done this one. There's another calculation I still haven't collected or found yet. And that is this guy. It's called the standard error, right? It's also the standard deviation, if you want to use that name. And it's a big, ugly formula. And it looks like this. P1 hat take away 1 minus P times 1 take away P2 hat. That's a long-winded way of saying it. Let's try this one. Plus P2 take away 1 minus P2. That's a nicer way to say it. Over into. You recognize that guy? Big ugly formula. Let's see what it is.
I think you accidentally wrote P2 hat in the beginning.
Oh, there we did. That's it. Thank you. So what have we got? We got a 0.75. And if you take that away from 1, you get the 0.25. And then you divide it by 400. And then you have P2 hat. So you get a 0.78. If you take that away from 1, you get a 0.22. And you divide that by 600. So I'll go to the calculator. And we're going to do the square root of 0.75 times 0.25 divided by 400. And then 0.78 times 0.22 divided by 600. And the answer I get is 0.027. Let's say we do things to 3 decimal places. So far, so good. Right. Now, what we're going to do is put that package together. And since you decided to use that one, I'll put a little bubble around it so I remember which one I'm doing. And here is our 99% confidence interval. It's P1 hat take away P2 hat plus or minus 3 standard errors. And this guy is negative 0.03 plus or minus 3 times 0.027. So that's negative 0.03 plus or minus 0.081. Can I just call it 0.08? Right, make it easy for me. If you take this away, you get negative 0.11. And if you add it, you get positive 0.05. And as a percentage, that's negative 11% to positive 5. So what we're saying is that the difference between these two groups could be as much as negative 11, which basically means this guy is 11% less than the other. But it could be as high as positive 5. And wouldn't positive 5 mean this is 5% bigger than that one? So conclusion time. We'll come back to this guy in a minute. If you have one of these compare P1, take away P2 things, right? If you get an interval that looks like this, negative 12%, negative 9%, right? Since all these numbers are negative, doesn't that mean that the first thing is smaller than the second? Agreed? If the interval of the difference is always negative, then it must mean the first thing is smaller than the second. That's why the answers are all negative. You could, however, get a positive 3% to a positive 7%. In that case, wouldn't that mean the first thing is bigger than the second? So wouldn't that be evidence that the first thing is bigger than the second thing? And then you get, unfortunately, you get this more than you'd like. Don't you get some intervals that contain 0? And when they contain 0, what do we say in that situation when our 99 or whatever confidence interval we picked has a 0 in it. What does that tell us?
That there's not enough evidence
That's it.
to prove.
That's the one. There's not enough evidence to prove that there's a difference. Not enough evidence to prove there's a difference doesn't mean that there isn't a difference. It just means we haven't found evidence to prove it, right? That's essentially all that means. Now, in this story here, would you agree we fall into the third category? So this would be not enough evidence. So this new cancer treatment wouldn't be considered proof that it does a better job than the old one. Barbara.
So can you explain that? What does that mean then? There's not enough evidence to prove. Yeah, I think you were just starting to explain it, to prove they're different.
There's not enough evidence to prove that these two numbers, these two percentage success rates, are different from each other. Different, they're not the same number, right? They're not,
Okay.
they could be bigger, one could be bigger or smaller than the other. We can't tell.
Okay.
Right? And the reason we can't tell is that since any number in this interval is just as likely as any other, couldn't the answer be -5%, right? Now, if it was -5%, wouldn't we be looking at this 5% less than that one? But couldn't it also be +3%? Wouldn't that make this guy now 3% bigger than that one? The total opposite result. If an interval only has negatives, the first thing is always smaller than the second. If the interval has only positive numbers in it, the first thing must be bigger than the second. But if they contain 0, right, some negative stuff all the way up to positives, there's not enough evidence to say that one is guaranteed to be bigger than the other, right? It could be one way, it could be the other, you can't tell. So that's what we mean. So in the context of this story, we haven't been able to prove that the new treatment does a better job than the old one. Technically speaking, couldn't it do a 3% worse job? And this could be the real difference. And if the real difference is 3%, the old treatment is 3% better than the new treatment. And that's the conclusion you could make, right? That's possible. We can't tell. It could be the other side as well. So in the FDA, what they typically do is they err on the side of safety. If you cannot prove that the new drug is better than the old drug, you can't produce it and use it. Now, it might be motivation to the pharmaceutical company to look at the ingredients and maybe tweak them a bit, make them more effective, and then try a different, a year or two later, try a different version of the drug, see if it can make a significant result. Does that help, Barbara? I'm not sure. Are you sure? Okay, very good. Now we're going to do that exact same calculation, right? This one here. And we're going to do it on salt, because salt makes life 10 times easier. So I hope I've got this thing set up. I have. So let's show you this in action. Go over here and let's put it the way you'd probably see it the first time you go in, right? So you click on it and it would look something like that. You go to this and you choose 2 sample proportions. You see that again? You click on it. And sample 1 in our case was the old treatment, and that was 300 out of 400. And sample 2 was 468 out of 600. And then confidence interval 99 and generate results. And the lower limit here is, would you agree that's probably 10%? Put my red pen, right. So negative 0.10, and at the other side, it's 4%, 0.04. If you want to know what the standard errors is, there's the first guy, there's the second guy. Now, if you wanted to know what the standard error of the difference, you'd have to do the calculation. So here is the comparison. We did it by hand and we got this. This is Salt's version. Do you notice there's a little bit of a difference? And that little bit of a difference was because they probably used this number here. Now, I'm not going to do it, but if you went through this calculation, but instead of times 3, you did times 2.875, you would be looking at these red numbers. So are we convinced that Salt and us do the same job? You agree that the slight difference is what constant they use. A side job before we do another one of these without the whole numbers thing. Suppose I had group 1, we'll do Scottish people, and group 2, we'll do Americans. And we did a survey to find out what percentage of Scots and Americans still smoke cigarettes, right? And then Scotland, we did 100 people, and 55 of them, adults we're talking about, still smoke. And Americans, we did that, and we did say 200 of them, and 80 of them still smoke. And just for argument's sake, we did a 99% confidence interval for the difference. Right? And the difference ended up being 0.5 to 0.15, which is what, 5% to 15%. If we in fact got that on a 99% confidence interval, that the difference between the two is somewhere between +5 and +15. Here's some conclusions I can make. First conclusion. P1 is greater than P2. Would you agree? Now let's turn that into English. Doesn't that mean the percentage of Scots who smoke is greater than the percent of Americans that smoke? Can you see that's what P is representing, right? The percentage of Americans that smoke, percentage of Scottish that smoke. So based on this analysis, can't we be confident that this is true, right? More Scottish people smoke cigarettes than Americans. Now, this is a 99% confidence interval. So in a way, aren't we only 99% sure that this is true? We're never going to be 100% sure, but aren't we darn close, right? What percentage of the time will I make this conclusion and end up being wrong? %1 of the time. Would you agree 1% of the time is not perfect, but it's pretty good, right? Statistics is never about perfect. It's about pretty good, right? We can do only so much, right? Because we're only working with limited information. Now, I can say something a little bit more than that in this case. Would you agree that all of these numbers are bigger than 5%? Right? 5, 6, 7, 8, 9, 10, all the way up. They're all bigger than 5. So I could tweak this a little bit and not just say that the percentage of Scottish who smoke is bigger than Americans, but I can say it's 5% more Scots smoke than Americans. Not only is it more, it's 5% more, at least. Would you agree? It's 5% or even more than 5%. doesn't that extra little bit give you a little bit more information? Because couldn't more mean it's just like 0.5% more, it's hardly worth talking about, or it's 40% more, which, whoa, that's a lot more, right? Probably wouldn't use it in this case, but I could. Would you agree that all these numbers are 15% or less, right? Couldn't we also phrase, I'm not writing this one down, but couldn't we say that at least 15% more Scots people smoke than Americans? Right? It's a bit funny, the English language, isn't it? At least, and it's a big number, right? At least 15% or more, right? Smoke, or less, I should say. I did a different story. I did French against Germans. And I did a 90% confidence interval. And we got negative 0.11 and negative 0.02. And it's the same question about smoking, right? So this is negative 11%, and this is negative 2%. Let's look at our first conclusion. These are all negative numbers, right? In terms of P1 and P2 then, what conclusion can we come to if the interval looked like this?
P1 is smaller than P2.
Agreed? And wouldn't that translate as the percentage of French who smoke is less than the percentage of Germans who smoke? Are we getting comfortable about how the interval gives us evidence about significant differences between two different populations? If they're all positive, we can say the first thing is bigger than the second. If they're all negative, we can say the first thing is less than the second. What's going to happen if we do the last situation then, where it's negative 0.11 and it's positive 0.05, right? That guy. Negative 11% to positive 5%. If you get an interval like that, aren't you really in trouble with what kind of conclusions, if any, you can make? In fact, isn't your conclusion going to be, we can't make any real conclusions? We don't know who's bigger or smaller, because it could go either way, couldn't it, in this interval? A lot of people think because there's more of this number and less of that, that somehow that is making it more likely, you know, that the negatives are right and the positives are not. The interval that you get, the only thing you can say for sure is the real answer is somewhere in that interval. And any one of the numbers is just as likely as any of the others. So plus 4% is just as likely as minus 10%. Right? And don't put any other significance on the fact, even if it's ridiculous. Can you imagine a story where it was minus 20% all the way to 1%? Would you agree that's almost all negatives? Even in that world, it's still, you can't tell. Because couldn't it be the 1% was the number that you've got? Your interval doesn't tell you really anything about anything else except it's in that interval, and, you know, live with it. So far, so good. So let's make a story and do a generalized result. Who should we pick? We need two things here. I think we could try picking this class, which means it will fail miserably, but that's fine. At least we'll try. Right? So you lot are going to be split into what groups? I have no idea. How many of you, I need this to split my groups. How many of you are taking an English class right now? 1, Yeah, checks and hats, right? So hold on. 1, 2, 3, 4, 5, 6, 7 of you. Okay. So group 1 are people who are taking English, and there's 7 of you. And group 2 then is going to be the rest of you who I'm just going to describe as not taking English, right? As good a way of describing you as we can. So there's 5, 10, 15, 20. I'm not counting myself, so there's 22. So 15 of the other group. Okay. We have tiny sample sizes, but that's fine because I'm going to cheat. If I use sample sizes for the first group is 7 and the second group is 15, would you agree that I wouldn't get any valuable information? Aren't those samples just far too small, right? So I'm going to cheat, and I am going to pretend that each one of you is worth 10 people. Okay, so now we need to ask a question about English. People are taking English and those are not. And I'm going to go for this one. How many of you in English, this is only the English people, so I'm going to have to go back and have the whole class so I can count these. How many of you who take English right now, oh, come on, there we go, have read a book in the last month? 1, 2. That's not good. 1, 2, 3, 4. There we go. That's better. 1, 2. There's 5. So 50 out of 70 of you have read a book in the last month. How many of you have not taken English have read a book in the last month? Great. Only one of you. No, I'm too slow. 30 of you. Right, got it. So we are now going to do an analysis on this. If I didn't catch you because you voted too slow, sorry. We got everything we need. We are going to find, what do you want, a 90, 95 or 99 to see if there's any significant difference between English students and people who don't take English? What do you want? 90, 95 or 99? That's all you got to pick. Which one do you want?
99.
99 it is then, okay. Group 1 were the English, and there was 50 of you out of 70 that have read the book. And I'm thinking you've read a book because your English class told you to. That's what I was hoping, at least. And 2 of you just decided that you didn't need to read the book because you already read it sometime in the past. And 30 out of 150 in the other group. Okay, you want a confidence interval, and you said 99, so I should be able to generate it. And the answer that we got is 0.351, so that's 0.35. And the upper limit is 0.676, so that's 0.68. That was pretty easy, isn't it? If you type in the numbers, you pretty much, the rest is kind of handed to you on a plate. Let's see what that looks like then. A 99% confidence interval. And that's somewhere between 35 and 68. And that just represents the difference between these two. If you want to see what those look like as percentages, 50 divided by 70 was about 71% of you. And this guy here is 20%. And what we're saying is that the difference between these two is somewhere in that range. Would you agree that statistically we have proven that people who take English read books more often than people who don't take English? Everything's positive. Couldn't we even say 35% or more have taken it? In other words, the difference is 35% or bigger, right? 35% or bigger. a pretty significant result. And then you could, I don't know, you could back it up by other storylines. Right. Next is going to be even more dangerous. I am going to go online and we are going to see if we can actually find somebody who's done a survey for us. And I'm going to click on this thing and let's see what we can do. Google. So click in and hopefully you could come up with something that we might be able to get some data on. Right, I'm going to put a search in a minute. We need two groups, two things to compare, and we need something that's, there's probably some data out there. Anything you're interested in finding out and see if we can get one. Okay, let me try some. Let's do COVID. Percentage. Of males vaccinated. Okay. No idea what this site is. So hopefully it's telling the truth. I don't have a business. That's probably. Oh, here's an article. Why is there such a gender gap in COVID-19 vaccines? So evidently there is a difference. Maybe it'll give me some numbers we can use. So there is the numbers are kind of hidden. Well, they have lots of percentages. Okay. So P1 hat is 95%, at least in that age group, and that is the females. And P2 hat is only 74%, and that is males. I guess all I need to know now is what kind of sample size did they get this from? And then they go in and come up with reasons. Okay, I'm going to cheat a little bit because I don't want to spend forever reading an article to get the data. So all I've really got here is the percentage. So let's just say that if you took a sample of 1,000 women, right, 95% of them would be vaccinated. And if you took a sample of 1,000 men, 74% would be vaccinated. That could certainly happen. Now, I know that's 0.94, but it's also 95%. And this is obviously 74%. Now, when you type into SALT, have you noticed it's out ofs that you need? You can't type into COVID 0.95 out of 1,000. It won't work. You can't even type in 95% out of 1,000 because that won't work. What you have to find out is what 95 of 1,000 is. So let's see what that would be. 0.95 times 1,000. Why am I doing that? It's easy to do. It's 950 people. So if you ever get a question and they tell you the percentage, will you find what the raw data is from that? So if there's 200 people and 82% did something, 82%, 200 is the number that goes there. So that's going to be the one group. And the second group is going to be the 740 out of 1,000. Do you think that's going to be, if it was 1,000 that we got the data from, do you think that's going to be significant? Do you think the interval for the difference is going to be positive numbers? It's going to be significant. Does that look a big enough difference? Any gut feelings about it? Get nothing? I think it's going to work, but I've been proved wrong, so let's find out. So I'm going to nip over to this fella, and the females were 950 out of 1,000. And for males, it was 740 out of 1,000. And I want a 99% confidence interval because I've decided that's what I want, and we'll generate it. And the answer is 0.17 to 0.25. So based on that very unprofessional way of collecting the data, I would say that there is strong evidence to prove that women do get vaccinated a lot more than men. And wouldn't it be at least 17% more? Could be as high as 25% more. And then I'm sure if I read the article, they'd go into why is that the case, and there's, who knows. But evidently that is the case. Anybody want to throw in 5 cents worth? Why do you think women get vaccinated more than men? You are allowed to be sexist in this. Why do women get more than men, right? As long as you do it in a respectful way. Why do you think there's a difference? Because there clearly is, right? Even in my data, there clearly is.
Because women have to stay alive to take care of their kids.
Okay, so women feel the need that they better be protected. Okay. And women feel very protective of their children, so they probably don't want to give it to their children either. Right. I could imagine that being the case. As good a reason as any. It could be that men are more stubborn than women, and you're not the boss of me. So they tend to rebel more when they're told to do things. Perhaps. Okay. There's really not an awful lot I want to do more today because I have some other business. Has anybody got any homework questions that they want me to go over before I leave so that we can get ready for the homework that's due this weekend? I think it'd be more valuable for me to do that for what time we've got left. So if you're good, say your name and bye-bye. If you've got some homework questions, you hang about and I'll deal with you. Okay? So we'll cut it short today. We're kind of ahead of the game, which is fine, so I don't mind closing a little early.
Thank you.
You're welcome. Have a great weekend. As I say, I'll hang about for those who have some homework questions that you want me to deal with.
I have a question for the chapter 9 homework.
Sure. Let me go load it up. And unless it's some very quick, which it probably isn't, because most of them involve a lot of writing.
I think this one's fast. I just don't know why I keep getting it wrong.
Okay, I'm almost
Yeah.
logged in. So give it a few moments more. We'll see what it is.
Yeah.
It's loading up as we speak.
Okay.
Right. It's better if I just find your version of the question because they changed the numbers. So who was it that was talking?
Oh, me, Crystal?
Right, I got you, Crystal. Gotcha.
Oh.
Right, I gotcha. Right. Which question number was it?
For number 1A,
In question 9A,
1A
right, what chapter?
in chapter 9,
There's 3 chapter 9s. Is it intro
Oh.
to sampling or A or B?
in B for sampling distribution.
Okay, and it's right at the top, question 1A.
Yep.
Okay,
Because I put -7%, but it said
You
that was
did.
wrong.
yes. Okay, I can see what you've done wrong. It's easy to fix. Your number was right. It's just the way you wrote it wasn't what they wanted.
Mhm,
They mentioned in the story that they wanted a proportion somewhere.
mhm.
And so the proportion should have been negative 0.07,
Oh, okay. Because I put -0.7. So,
right?
okay.
So, right. So at 7%, yeah, or negative 7%, yeah, but
Okay.
they don't want a percentage. So you have to do negative 0.07.
Okay, that makes sense. I was writing 0.70. Okay,
Right.
thank you.
Anything else? Anybody?
I had a question on number 4. It was 4F on the same test.
4F on the same homework?
Yes.
Right. I think it's quicker if I just do the general one then this time. 4F, if it's a specific number, I'll come to that. Right, see, oh, the big long question. Right, let's see. Using your knowledge of how to find areas under normal curve, which basically means using salt, find the probability that P1 take away P2 is less than 0. In other words, find the probability that the exit poll shows a lower number, a lower proportion of voting for candidate A in the morning than the day. So you'd already found the difference, right? What was your
Yes.
difference as a number?
My difference, let's see. The mean is it, no, not 0.52. 0.03, I think is what I have.
Okay, yours is different from one I'm reading, but that's fine because it could be because your numbers are different, right?
This
So
is that you're asking for
right.
the mean of the P1 minus
so
P2?
yeah, you're doing P1 hat take away P2 hat,
Yeah, okay.
right? And what
Yep.
did you get again?
0.03.
0.03, right? I'm going to kick over to the picture now, kind of show you what you're basically interested in finding. So you're trying to find the chances that it's less than 0.03, right? Now, in this story, it's a normal distribution. The mean is 0, because the mean is basically
Mhm.
assuming that they're equal. The standard deviation would be the standard error. So you'd already calculated somewhere else that standard error. didn't you? Do you
Yes.
have that number?
Yes, that I have is 0.0316.
Right, and then I'll put in that number 0.03 again, right? And the answer I'm looking at in this case, you said 0.03?
For the difference is
Uh-huh.
0.03, and then the standard deviation was 0.0316.
Okay, so the answer I'm looking at, can you see this guy now?
Yes.
So the guy I'm looking for is, that guy is 0, because the difference is 0. That's the standard error, I'm assuming that's correct, and that's the 0.03. So the answer you're trying to find is this guy.